All right, can everybody see my screen?
Yes.
Okay, so what are these right here? These are the cell lines. Okay, Shirley is there too. Great. So we have the cell lines, and these, you can't really tell by these names, but some of them, if you look through, these are different drugs. So for example, doxorubicin is a pretty well-known drug, and Gifitinib and others. So if you want to know about these, for example, let's just Google it. This is, by the way, the paper that I sent over called Glycoproteins in Cloud and Low Breast Cancer Cell Lines Have a Unique Expression Profile. As you read through the paper, it actually also talks about the different drugs that were effective for these cloud and low cell lines. So right here, drugs most active against cloud and low cell lines. So take a look at that. You already have the RNA-seq data, and we already did a lot of comparisons between cloud and low and normal-like, which should give you a sense of what cloud and low versus other types would be as well, because normal-like represents kind of like, I guess, the average, something that is normal-like. And we already talked about specific features of cloud and low, so that Claudin gene. So now we can look at this drug real quick and just see what this is to get a sense of what we are going to be dealing with. Okay, so you can see here it's a chemical compound. You can buy it here, and here's some publications. So 17-AG suppresses growth and invasion of lung. So it is used probably for a number of different cancers, but here's a specific clinical trial. And I think it's interesting to understand how these drugs get discovered. What exactly do they do, their mechanism of action, and then how are they planned to use? So, for example, here you can see that HSP90 inhibition is effective in breast cancer, phase 2 trial of this drug that we have right here, plus another drug. And I think that we also have this drug in the table. So let's just search for it real quick. Maybe not. Trastuzumab. I believe I saw something at least similar to that. Okay, maybe not. But what we do know is that you can see here HSP90 is a chaperone protein, and this is a natural product that binds to this and inhibits its activity, inducing degradation of these clients. In preclinical study, HER2 is one of the most sensitive known client proteins. On the basis of these data and activity, we conducted a phase 2 trial with another drug, and this is for HER2 positive breast cancers, right? And this is specifically for metastatic HER2 plus breast cancer patients. So this kind of gives you an idea of what you should be expecting. So if we were to take a look at, I believe what we would want to do is take a look at the class, so the different subtypes of breast cancer, right? So I believe this is 184A. Let's see, This is going to be the IG50. So you can see that this actually includes a subset of cell lines. So we don't have all of the cell lines, and we want to be able to understand something and then compare to the publication. So what I wanted to do today is, as we familiarize ourselves with the data set, what we have and what is the objective, let's try and together discuss how this could be turned into a project. So what would be the steps of analysis that we should do for this kind of a data set, right? To understand, the goal would be to understand which drugs are more effective for some specific subtype of breast cancer, right? So on one hand, we have the capability to separate patients or cell lines into subtypes based on, for example, RNA-seq data. On another hand, we then have the ability to treat those cell lines or patients with a specific drug, in some cases more effectively, in some cases less effectively. So let's try and talk about the steps of analysis that you would have to do to achieve this goal. Who wants to go first? So either you can volunteer or I can ask somebody to start. So if nobody wants to start necessarily, I'll just start with Baby Satravade. Do you want to share with us what you think about what you understand from the data set and how it could be used to select drugs that are more effective for specific subtypes, as opposed to just a drug that might have generally good or not so good inhibition?
Like, are you speaking about this data set?
Yep, this data set.
Maybe we'll go for the toxicity analysis to predict which drug is more effective or not.
So
based on the scores.
Based on what?
Scores.
Okay. So what is this score? What are these numbers?
Sorry, I'm a bit confused.
Okay, well, this is inhibition of growth, IG50.
Yeah.
So one of the major characteristics of cancer is proliferation of cells. So what we see here is how these different compounds hinder that proliferation of growth. So they stop the growth. So how would we use these numbers to understand which drug or which drugs would be more effective for specific subtypes of cancer? Okay, so baby, I understand it might be a little bit confusing at first, so don't be, anxious about it. It's fine. I'm just trying.
I'm completely sorry. I just came out, so I'll get back to you later. I'm so sorry.
No problem. So let's see what people are writing here in chat. Kian is saying, We need to know their relationships with one another. So that means we have to do what we talked about last class, the Bayesian network. Vaishnavi said select drugs with lower IG50. So let's talk about some of these ideas real quick. So let's say I have a drug, right? And it obviously has different levels of IG50. So the first thing that I can do, in fact, is I can just select, for example, all of these and based on cell lines, right? And let's just look first, explore our data, and let's see what is it showing us, right? So here I have levels, and obviously I can see some difference, right? So for example, I can see that for KAMA1, HCC 1428, the IG50 value is high. Okay, so a high IG50 value would mean that it is more effective. A low value, like here, for HCC 1187 would mean that it's not very effective. So now the question is, okay, I know that I have some range, I have some effective, some less effective for this drug. Now I have many drugs and many of these scores. What specific methods can I use to distinguish between some subtypes of breast cancer? So now somebody suggested here Bayesian network. So what does a network analysis give us? Network analysis gives us how one might be a result of another. So if I have multiple steps from one object to the fifth object, I can not only establish the relationship between the 1 and the 5, I actually know that 1 goes to 3, 3 goes to 4, 4 goes to 5. So that could be an interesting sequence. I think in the same way, we often think of pathways. Why are pathways interconnected in a specific pattern? Because we know that the effect of inhibition, for example, on one gene could lead to a sequence of events. And so network analysis could be used in either time series data, or it could be used in, for example, those biological events that we know have some kind of a sequential thing to them. So that was Bayesian network. The other network was a Markov model network, where we know that things are interdependent. So combinations of pairs, for example, are interdependent, but they work in multiple pairs. And so sometimes we know some, but don't know others. And so by knowing some, could we then infer something about others that we don't know? So I don't think necessarily that's relevant here, but let's think about other methods that we know to select relationships, define relationships between subgroups or groups of features and objects. How could we think of this table as a table that represents these kinds of relationships? And what methods would you apply, and in what sequence, to identify which drugs might have more efficacy for some subtypes or subgroups of these cell lines? Who would like to answer this question? Okay, so I'll ask Sushma. Sushma, would you like to answer this for us and just share your thoughts or questions about this problem statement? Sorry, I can't hear you very well. Maybe if there's an issue with sound, do you want to just type it in chat so we can all see it there? Okay. Okay, so yeah, if you can type that up, and we can talk about the answer. Okay, so I think I also have here you can see here some examples. If everybody can see my screen, I think we have already talked about how there are classes that we can incorporate into this table for different cell lines and for different subtypes that represent breast cancer subtypes. So probably, the first thing that we would want to do is we would want to add that information in here, right?
Can you hear me right now?
Yeah, this is much better.
Yeah, I think maybe like if you go for the clustering, I don't know whether I'm right or wrong. Like you were asking the drugs effective for the subtypes, right?
Yeah.
So if we go for the clustering, we will know the based on the IG50 value, we will know the drugs that are effective for the particular subtype of the drugs. I mean, breast cancer cell lines. Am I wrong?
Well, let's talk about clustering. So we have this proposal to perform clustering. What would I get as a result of clustering? So if I take this table and I do clustering, what would be the result?
If you go for the hierarchical clustering, you'll get a dendrogram.
And what will that dendrogram show? And about what? What would be my objects that I will cluster? Would those be cell lines? Would those be drugs?
Maybe if we give the cell lines and the drug classification, maybe the I'm confused.
Okay. Okay, who else wants to try and answer this question? How about Vaishnavi?
Can I answer?
Sushma, go ahead, yeah.
Yeah. Maybe if we go for the k-means clustering, it's based on the centroid, right?
So k-means clustering of what? Of cell lines, of drugs? What exactly will we use?
Sorry, we can't use that actually.
Okay, so Vaishnavi is saying here PCA. So, okay, what will we do PCA of? Vaishnavi, do you want to expand on that? Okay, so as Vaishnavi is putting together her thoughts, we have the idea of PCA, so principal component analysis, to understand which drugs would work for which cell lines, right? Cell lines as groups. Okay, so can you, Shirley, can you expand on that? What are you trying to say? What do you mean by cell lines as groups? Okay, yeah. Okay, so your answer is that we should cluster the cell lines into groups, right? So we want to understand which cell line belongs to which group based on these IG50 values. And then Vaishnavi suggested that we use hierarchical clustering. So let's say we do that, and now we know which cell lines are in which groups. How does that help us understand which drugs are effective for which cell lines? Do you want to talk about that?
A specific group of cell lines will have similar type of drugs.
How would you see that? So you do clustering, right? So if you remember, how did we do clustering? We got something like, so let's, I've got some presentation here open. So let's just take a look here at the results of clustering. So let's see. So this was hierarchical clustering. So hierarchical clustering gives you something like this, right? So these are names of cell lines, and there's some relationship between these cell lines in a dendrogram. Shirley is saying here, I think a group of cell lines would have similar IG50s. So IG50 values are kind of like expression of gene values, right? So we can group cell lines together, that's true, but how do we know? So let's say this group or this group, how do we know whether this group, which drug is effective for it? That's the question. Okay, so Sushma is saying if we can get the group of drugs for a specific cell line. So yeah, that is the question. How do we get a single drug, a group of drugs that is more effective or less effective for some cell line? Just like I showed you in here, right? So if we take a look at the this drug right here, 17AG, we know that this drug is more effective for some, right? So all the high values, and less effective for others. So now I'm interested in understanding for each drug, how can I know which drug is more effective or less effective for which subtypes of cell lines? Because I'm not interested in individual ones. I'm not interested in just T47V, for example, or this one. I'm interested in general. So there are some subtypes, there are some drugs. How do I select between the two? How about, Kian, do you want to try and answer the question?
Sure. So your question is, you want to know how to separate between whichever one had the higher IG values. Could you do like a decision tree type thing to set like a threshold to like depending on the expression?
Depending on what?
whatever the level of IG was.
Okay, so let's think about this together. So you are saying we would use a decision tree. What would be our objects?
Object would be the drugs, the different IG levels for each drug.
So there's objects and features. Levels of IG50 would be what? So IG50 values would be used as what?
I'm not sure. I don't really understand your question.
Well, in all of these methods, you have observations or objects. An object is defined by some characteristic. Okay, so
Yeah.
you have three options. You have drug name, you have cell line name, or you have the level, IG50 level. So
Right.
can you walk me through what is an object, what is a feature, what is a characteristic of that feature for that object?
Well, I guess maybe I misunderstood, but if you're just trying to get the highest level of IG, could you not just filter out and like set a threshold based on you only want to look at the ones that are like the highest or like at a certain level that you know is meaningful?
Okay.
So I thought like a decision tree, since you can put it on like one dimension, then you could do the threshold and then continue to do the rest of your analysis.
So I understand the decision tree. It's a good suggestion, but I'm just asking, okay, so Shirley is here saying object is the drug, characteristic is the level. Yeah, so the object here, and this is important because you need to define when you're doing any kind of analysis, what is going to be your rows, what is going to be your columns, what are you trying to analyze? So you are trying to analyze cell lines because you are trying to say that the cell lines, right, they were affected by a drug. So this drug affected this cell line. How? Like this. That's the characteristic. So now you want to understand for which classes of cell lines, right, do I have specific drugs? So if I know that some drugs are more effective, right? So more or less effective is characterized by this number. And I know that the grouping that I'm able to define is for cell lines, right? So I can use RNA-seq data to define classes of these. I don't know the classes of these, right?
Right.
So that's why these are going to be my objects. I am interested to study these in the context of these values. So now we have this suggestion of decision trees. What type of a method is a decision tree? What does it do? What does it do, Kian?
Oh, a decision tree?
Mm-hmm.
A decision tree is a way of it's a classification, not a clustering. Well, like you said, like it starts at to see what values are significant if you remove or keep them, and like it helps with setting thresholds.
Yeah, classification. You said it right. It's not clustering. It is classification. So that's important to remember. And Shirley is saying, choose a feature that can separate the data set. Exactly. So that's why we are looking at, for example, decision tree is a good classification option here because it will also tell us based on which feature, right? Based on which drug. Okay. So now let's say the analysis goal, is it clear what the analysis goal here is? So we want to understand which drugs are more effective for some specific class of cell lines, right? Is that clear to everybody, or does anyone have any questions about the problem statement? the objective of the analysis?
No, it's clear.
Yeah. Okay, so for everybody else also, if anybody else has a question about this, please let's make sure that this is clear, because what I will be asking you to do is to start planning your analysis, right? So that would be your project. Again, the reason why I gave you this table and the reason why I gave you that paper is because I want you to try and read through the paper, understand how the authors of the paper, what did they do? They took the same data set that we already know, right? And they took a specific subset of cell lines. They're called Claudin-low breast cancer cell lines. And they studied them from the RNA-seq level, and they talked about Claudins, which of course define Claudin-low, and they talked about other genes as well, where they were able to understand that there's a specific profile of expression that is specific to Claudin-low class of cell lines or patients. And also there are some drugs that are more effective or less effective specifically for Claudin-low cell lines, right? So right here, as I was showing you before, they identified specific cell lines that were more effective against Claudin-low cell lines, most active. So now you have the same challenge. You have a data set. You've got the RNA-seq data set. You have the IG50 data set. And your goal in your analysis is first to plan, how will I go from the data that I have to some kind of a reasonable insight into how specific drugs are more or less effective for a specific class of cell lines. Okay, so that is the objective of our next assignment. Okay, so hopefully that was clear to everyone. Just to give you an idea about how this is, you know, how I would approach this. Okay, so I will give you kind of some ideas from my side, but you know, you're not limited to that. So obviously, the first thing that you want to do is you want to run some exploratory data analysis. So let's delete this. Or, okay, so what do we see here? We see here that the minimum value is going to be kind of where it's not effective, right? The maximum value will be where it is more effective. And what I can obviously do is do some, you know, extract some minimum, average, whatever. So for example, if I know the average, so this is going to be just, you know, trying to understand my data set here. So what I can do is I can, you know, just kind of look at these summary features, and I can see that, you know, average, on average, you know, there should be a clear separation between this. So which means that, you know, I should be seeing some significant differences. And the other thing that I can, of course, do is organize these cell lines by a specific class, and that will give me a better understanding of how class is related to this efficacy. I have some unsupervised methods as well, right? So it was mentioned already, PCA, principal component analysis. We mentioned clustering. Both of those are unsupervised methods. So what I can do is I can probably run those methods to understand better my data, whether it naturally groups into something. So for example, if I did PCA and I saw groups of samples together by class, so samples here are cell lines, and I see those cell lines grouped by their class, that is good because it means that actually all of these drugs act in a subtype specific manner. But maybe I won't see that. Maybe I will see that actually PCA is fairly random, which means that most of these drugs have a very general mechanism. Their mechanism is either effective or not effective for the majority of the cell lines. But probably through all of these, there will be specific drugs that do have a specific target, and they do influence some cells, but not others. And you know, I think here there's some example where we can see where we can see some of this, right? So, for example, MG132, it looks like is probably more effective for normal-like. You know, and you will see that the difference is not going to be that great, but you will start seeing some differences, even though they're smaller ones. So here, you know, I was able to select some, and let's just take a look at this real quick. What could this mean? You have the normal-like, you have the luminal, cloud and low, basal, and averages of all of them. Actually, these were only a subset of drugs. So, for example, what can we say about the first one, docetaxel? Well, we can see that on average, right? So this middle line is going to be our median here. So we see that on average, it's kind of the same, effective across different cell lines, exactly. But if we look at the blue one, right? So what is the blue one? The blue one is MG132. What can we say about it looking at this chart? Shirley, what do you think? Is it equally effective across all cell lines? Or is it more effective for, it's less good compared to the green one, so it's less effective compared to the green one. But is it more specific? Like, does it, yes, so it is more effective for normal-like. So now if I see my patients and I'm saying, okay, these are normal-like ones, so maybe MG132 is a pretty good option, right? And maybe docetaxel, which is maybe good for all of them, but maybe it's more toxic. So maybe it has more side effects. So maybe that's why it's not universally used, even though it's so good, right? So if that is so, that it's got, you know, a lot of side effects, now I have a different drug that for normal-like patients works pretty well. So I will be interested in that kind of a difference between here it's pretty good, here it's less good. What about some of these other ones? So do we have here an example of a drug that seems to be, you know, also just more effective for a specific subtype? And what other considerations would you have from seeing this chart? I mean, what other things could you be thinking about? Because obviously we're not just looking at on average how it is. It is low overall, yeah. So some of these are fairly low, but also you should, yeah, so some of them are not so great. Maybe they're good for like other subtypes or other cancers. You know, maybe they tried something that is good for like lung cancer, and we know that it's not going to be good for breast cancer. But what other things do we know here? Well, we know actually, you know, look at this one, for example, right? You have some of these outliers that represent that it worked really good for them. But actually, for some of them, it didn't work that great either. You know, you can take a look at over here. You've got a lot of variation. So some of these have a lot of variation. So even though I might think that, look at the green one, it's kind of on average good for everybody, but for some, it's actually going to be not as effective as, for example, this blue one, MG132. And even not as good as, for example, this one, which is XRP44X, right? So even though on average, I see some trends that, you know, will make it difficult for me, I now know that, you know, it's a whole range, and within that range, I have probably a more patient-specific decision that I could be making. So these are some examples that I did. So how did I do them? Briefly to summarize and for you to think about your own process. What I did was I, you know, looked at the classes, so subtypes of breast cancer that I know for different cell lines. And then I used classification and feature selection to be able to understand how drugs help separate the samples into specific subtypes, into specific classes. And then feature selection told me what types of features. Now, if you remember how feature selection works, there's pretty much, we talked about decision trees, random forest as an example. There's stepwise LDA. So there are several methods that we can try here. But the problem is that I can get a very small number of drugs. So I can get, for example, from stepwise LDA, maybe 4 or 5 that, yeah, so I think this is stepwise LDA, selected drugs. So what you can see here is some variation. So for example, the first one, bosutinib, you can see that it's going to be better for normal-like, not as good for luminal, and then okay for cloud and low. For this one, right, this is tricostatin, you can see that it's actually the best, or sorry, maybe it's this one, erlotinib, is the best for normal-like, and then not good for luminal and cloud and low, and a little bit better for basal. And so forth. So, but the problem is that you have only 4 of these. So then what I can do is I can probably do stepwise LDA, but I can also do random forest or even random forest multi-run, and I can get a more expanded number of features. So this would be what I got from random forest. From multi-run, where I did more than 5, and here was regular random forest, more than 2. And I highlighted here some of the ones that I also found with stepwise LDA, so they're actually present here and here. And that's interesting that they are highlighted, right, because I can see that that's probably a pretty reliable way to do that, right? So if different methods give me similar results, that's a sort of a cross-validation, as well as doing it on multiple subsets, which is actually what step forest or random forest multi-run would do, right? So these are some examples of what I did. And of course, the process was, 1, add class information to cell lines, use cell lines as objects, IG50 values as characteristics of features of drugs as features, and then run analysis using, first of all, exploratory data analysis to understand where the differences naturally exist and what are some characteristics here. And then also perform classification with feature selection, so I can select drugs that are most specific. I'm looking for specificity here, right? So that is the objective. And then I obviously visualized the results and try to understand what does that mean for these different objects. The last step, and here we might have two, is to try and understand what is the biological relationship. So if I know that one of these drugs, like for example, docetaxel, happens to be, it appears to me that it is most effective for luminal. Why is that so? What kind of a biological explanation could we have for that? The other way of doing it is, of course, looking at if luminal has a specific gene expression profile that is unique. And I know that this has a IG50 profile that is unique. I can get a bunch of genes that behave in that way, and I can get a bunch of drugs that behave in that way. So how do I find drugs that are similar by their IG50 profiles to this drug? Now I can do clustering. Now I can do work on selecting similar things. So that's what we are trying to kind of plan out and try. So obviously you've got the tables, you've got the data sets. What I am, we are going to be available to discuss the questions or the ideas that you have. But what I'm looking for specifically as deliverable over the course of the next, I believe we have 2 or 3 weeks left in this course, is a plan, a written out plan. It could be, 1-page long plan of how you would approach this with some idea of, I've done this, I kind of understand what the input and the output is, what I need for that. So if you can try and start working on that and create a draft that we would be able to discuss. Now, if you want to understand how other people approach this same kind of a project idea, you can refer to this publication as a reference. So again, they set out to understand the same thing that we set out to do, right? So how can we define a specific subtype of breast cancer? And so they defined cloud and low. They focused on cloud and low. And then they went through the drugs and looked at what might be the reason why some of these drugs were more effective for cloud and low. So please read through this paper as an example. Try to understand what they did and what they found. I think it's very interesting what they found. And let's, next time we meet, start talking about some of your ideas and what you've been able to try with the data set that you now have, and what kind of results are you getting. Does that make sense to anyone, to everyone? Do you have any questions about this? Okay, well, if there are no questions, hopefully you can share this information with whoever was not present today. We are going to be available to discuss any questions that you might have. And if you don't have any kind of data that you think is needed to achieve this, please let me know. We'll see you again next week. All right, thank you guys. And I'll talk to you next week then.